So now we can see if we look at the top here, we have now aligned the point clouds. We're now not like the blue wall here is not further back compared to the yellow wall. We can see that we're now aligned the 2 point clouds here. Because we're estimated transformation, we're just applying that transformation to our point cloud, and now we can see that we have actually estimated a really good transformation between those 2 cameras. Hey guys, welcome to the video on this point cloud tutorial. In this video here, we're going to do visual odometry with RGBD images with Open3D. So in the previous videos, we talked about visual odometry with a monocular camera, but also with a stereo camera. We used Open3D to do some different kind of like feature extraction, feature matching from image to image. But in this video here, we're just going to use visual odometry with RGBD images that we can get from, like, for example, different kind of depth cameras that I'm going to show. And then we're going to use Open3D and implement the methods in Open3D to do odometry from these RGBD images. But first of all, remember to join the Discord server. I'll link to it in the description here. You can join the channel, chat about computer vision, deep learning, AI, and so on. You can also become a member of the channel if you want to support the channel with a small amount of fee. Everything will go to create more and better quality content here on the channel. Also, if you're a member of the channel, I can also help you out with some of your own projects if you have some problems and give some guidance. So if you're a member of the channel, you can join my private Discord server. We can talk about things. I can give you some guidance. So thank you guys. So first of all, here we just have a couple of slides where I'm going to show you the result from visual odometry, what the different kind of applications we can use visual odometry for, and also some different kind of examples of 3D cameras, so we can actually like get the RGBD images that we can then use directly with Open3D. We can also use Open3D to, for example, generate a depth map, so we both have an RGB image and a depth map, and then we can combine that to an RGBD image, and then we can use that in the Open3D functions and methods here that I'm going to show you throughout this video as well. So here we can see the results from visual odometry. So basically the idea behind visual odometry is to estimate the pose of our camera when we're driving around in an environment, for example, or we just take like images from different kind of angles. We try to move around, and then we try to estimate the pose from the different kind of point that we have in our image, so we can see similarities between images, and then between those similarities we can actually estimate the pose of our camera. So in some way we can create a trajectory around in the environment. If we're just having a camera, we're moving around, then we can estimate the pose and thereby the trajectory of the camera. It could be attached to a car, a robot, or so on. So here we can just see some of the results with the ground truth labels and also the estimated trajectories, where we can see we have these really nice paths here that we're actually able to estimate by using like visual odometry with both a stereo camera but also a monocular camera. So some of the applications for using this visual odometry is for, like, for example, self-driving cars, also robots. We can use it for space exploration. So if we just put a robot on Mars, we might have a camera attached to it, so we can do visual odometry, navigate around in the environment, because it can also be used for example, mapping of environments. We can have a robot driving around in a warehouse, doing visual odometry, trying to see where it can reach in that actual like environment. So we can use both for mapping environments. We can also use for localizing the robot. Where is it in the environment we're driving around? We're estimating the pose, and then we can try to localize that robot at a specific time. So there's a tons of different kind of applications that we can use visual odometry for, and it's also really easy because we basically just need a camera attached to something that is moving around, and then we just need to implement our algorithms. Most of them are already implemented. Again, all the code will be in my GitHub. I'll link to it down in the description as well. You can just go in there, take the code directly, try it out yourself, and so on. And also check out the videos about visual odometry with a monocular camera and also stereo vision camera. I have also uploaded that to GitHub, and I have videos about that here on the channel, where we go more in depth of what is visual odometry, what is the pipeline of visual odometry, and how we can actually like implement the methods here ourselves in Open3D with Python. So the last thing here is basically just some examples of RGBD cameras. So we can, for example, use like RealSense or the PrimeSense camera here. So basically just a camera where there is also like a 3D scanner, so we can also get depth information about our environment. So we both get an RGB image where we have 3 channels, one for the red color, the blue color, and the green color, and then we also have a D channel, which is the depth channel. So basically we just have an original image, or like a standard image as we know with RGB, and then we just have a depth image attached to that color image that we have. So then we have 4 channels in our image. We have the 3 color channels, and then we have the depth channel, and then we can just use that directly with the methods implemented in Open3D to actually do pose estimation of our camera. So we can try to estimate the pose, or like try to estimate the trajectory that we're moving around in the environment. So let's just jump straight into code here, see how we can actually implement this with Open3D. So in this example here, we're just going to take in 2 images where we can then create point clouds from those 2 images. Then we try to do post estimation of those 2 point clouds as we have already done throughout this video here. But in this video, we're going to have focus on doing it with Visual Odometry instead of ICP registration or something like that. So here we're just going to take 2 images. You can also take an arbitrary number of images just to have a while loop running. You can just keep loading in images in the while loop, applying these methods here, just appending or like calculating your estimated pose. So that will just be your current pose multiplied with the estimated pose, and then you just reach the new pose. You can basically just have a full loop running with just taking in your images, trying to estimate the path or the trajectory that your robot is driving with your camera attached to it. So first of all here, we're going to implement the different kind of modules that we need. So we need the most important ones here is the Open3D and also NumPy. So we can do our operations. We just import Open3D as O3D. Then down here, we're just going to import something from the tutorial here so we can create this interactive window. So when we draw and display our point clouds, we can actually like play around with it. We can try to like flip it around, zoom in and out on a point cloud and so on. So we're just going to hit shift enter here to actually like import our modules. Then down here, we can see that an RGBD odometry here finds the camera movement between 2 consecutive RGBD image pairs, as I just told you in the slides. And the input here are 2 instances of this class here, which is basically just RGBD image. The output is the motion of the form of a rigid body transformation. So it's basically just a transformation, how to get from one camera to the other. So how we act like, how is the transformation between those 2 consecutive frames. Again, you can just keep applying this to new frames coming in from your camera. Open3D implement the methods of these 2 papers here. You can just read more about that if you want to. First of all, we need to read in the camera's intrinsic parameters because we actually need to project out our points. And also when we're going to create a point cloud, we're going to create our point cloud based on our camera intrinsic parameters. So we get the absolute distances in the real world instead of only like relative distances. So first of all here, we're going to read in the camera intrinsic parameters. We're just going to use some defaults that is already provided here from Open3D. So if you're using like the PrimeSense default camera sensor to capture images, it is already implemented here. You can just go in, call here from O3D camera dot pinhole camera intrinsic parameters dot PrimeSense default. So this will basically just return the cameras and like the pinhole, the camera intrinsic parameters for the PrimeSense default camera here. We're just going to print it so we can actually see that we get the camera's intrinsic parameters out. So here we get the camera intrinsic matrix. We have the focal length here in the X direction and the Y direction, which is the same. So we have a focal length of 525 in pixels. And then we also have the optical center offset here in the X direction and in the Y direction. So now we have the camera's intrinsic parameters that we're going to use to actually like create a point clouds from our RGBD images. Down here, we're going to read in the images. So this code block here reads in 2 pairs of RGBD images from the Redwood format dataset. We can also see the dataset here, but basically Open3D has already implemented this dataset here, or like actually like implemented it and stored the dataset here inside of Open3D. So basically they just have a module here called data. So we just go inside open3d.data.sample redwood RGBD images. Then we just have all the images here stored in this variable or like in this object. And then we can just read in like single images from this data set. We can also just loop through the whole data set. We might create another video where we're going to create that while loop and just reading in images over and over again, trying to estimate a path in our environment. So here we're going to have a source and also a target color image. And we're also going to have a depth map here for source and the target point cloud that we're going to create. So we're just going to read an image. We're just going to take the serifed element of the color path and depth path. And down here, we're going to take another image. Then we're just going to take index 4. So we're going to take the serifed frame and the 4th frame. And then we want to try to estimate the pose between those 2 consecutive frames. So we're just going to run this block of code so we can see what is going on and go to the next step. Where in the next step, we now have the color image and we also have the depth image. And then we can combine that into our, as we saw up here, we have this RGBD image class. We're going to convert it to that. So we just have this RGBD image dot create from color and depth. And then we just return it to the source and the target. And then we can also create a point cloud so we can actually like visualize how different the 2 point clouds are, because we captured those 2 point clouds from two different angles, so we can see how are they related to each other, how are we trying to estimate. So when we do the transformation, we can actually like align the point clouds as well, because we know how long have we traveled and how much have we rotated from those two angles that we captured our RGBD images from. So we're going to create a point cloud here as well. We're just going to call a geometry, Open3D geometry.pointCloud.create from RGBD images, because now we have the source RGBD image and the target RGBD image, and then we just pass that into the function and it will create the corresponding point cloud. We also not need to pass in the pinhole camera intrinsic parameters that we just loaded in the previous block of code. So now we can run this one here, and now we have the source and the target point cloud and also the RGBD images that we will then use to call the Open3D function to do visual odometry. Here we're going to create a helper function that just visualizes the two point clouds, so we can actually like see what is going on before and after we're running our visual odometry functions here from Open3D. So we're just going to run this block of code here again, and then we're going to go down, compute the odometry from the two RGBD image pairs. So first of all, here we need to go into the pipelines and we need to set up our odometry option. Again, we just set it here, we initialize it here, so we have our odometry option. We also need to set up our initial odometry. We're just going to go with identity matrix, so we're just going to have ones here in the diagonal, and then we have a 4x4 matrix with ones in the diagonal, and then we're going to print out the option. So here we're just setting up our things here before we can actually like do our visual odometry here from our RGBD images. So we're gonna hit Shift Enter. We can see that we initialize our odometry option class. We have an iteration number per pyramid level. So we have some different kind of like pyramid levels that we initialize for doing our estimation. We also have a max depth diff and min depth and max depth. These are just the default values when we call this odometry option up here at the top when we want to initialize our visual odometry. Then we can draw a result here. So we draw our 2 point clouds so we can actually see what are we trying to estimate the poses between, like what transformation are we trying to estimate. So now when we hit Shift Enter, we actually get up to 2 point clouds here. So we have the source point cloud and we have the target point clouds, and then we can see that these are actually like point clouds captured from different angles. So there's a small change here in the point clouds. We can see here just the best way to visualize here is actually just to see how the walls here at the background is aligned. So we can see the yellow point cloud here, or like the yellow wall is a bit further back than the blue wall because it is just captured from another angle. So think that the blue point cloud here is closer than, so the camera has actually been further away here than the yellow camera, or like the yellow point clouds that got captured by that image. We can also see we have an offset here down at the bottom, at the floor, but we can also see some differences here in the chair. So the idea here is to direct like want to align these point clouds here, estimate the transformation from one point cloud to the other, because that will be the actual like path that we have traveled with our camera with respect to each other. So now we have the results here drawn. We know what is going on. We know what we're going to do. Now we can actually just set it up. We have two different kind of approaches. We can use a call-it approach, and we can also use a hybrid approach. Down here again, you can just read up on these different kind of algorithms that it's implemented by Open3D. It is basically just implementing algorithms from different papers. So first of all, here we just go in compute RGBD odometry. It is basically just a function implemented in Open3D already inside of the odometry module. It will return if we can actually like successfully estimate the trajectory, or like the pose, the transformation of our cameras. Then we're going to pass in our transformation caller term, or like this is what it's going to return. So this will be the transformation between those two point clouds that we pass in, or the RGBD images that we pass in, and then we also get some additional information. So we need to pass in the source RGBD image and also the target RGBD image. We need to pass in the camera's intrinsic parameters, and then we also need to pass in our odometry initialization, and also what type of function or algorithm do we want to use. So we're going to use the RGBD odometry Jacobian from the caller term. Down here at the bottom, the only difference there is that we're going to use RGB odometry Jacobian from the hybrid term here. We also need to pass in the option that we initialized up at the top for our odometry. So when we run this here, we will actually like do the estimation of our transformation between those two cameras with two different kind of methods. And now we're going to do to show what is the results from these two algorithms here that we ran, and how are we actually like estimating to the transformation of our cameras. So again, this is for 2 consecutive frames. You can just keep on doing this here for additional frames. You just need to pass in a new target frame, and then this target frame here will be the source RGBD image, and then we will read in a new image, which will be our target. And then again, we just have a new transformation. We just multiply that transformation with the previous transformation, and then we just keep on doing that. And then we will actually like just have a path generated, or like a trajectory generated from our camera moving around in the environment. So here we can just read about the different kind of stuff from the odometry option with the max depth diff and the min depth diff. So we can just read about those parameters if we want to change those. But in this video here, we just went with the default ones. We can also now visualize the RGB image pairs and see what is the results of our visual odometry here from Open3D with these 2 RGBD images from the Wetwood dataset. So here we can see that, first of all, again, we have already converted our images here to point clouds and rendered them together. So here we can just go down if our success color term here is true, which is the case that we returned up here at the top. So if these 2 variables here is true, then we're actually like able to estimate the transformation of our cameras, or like the images that we got in from our cameras, and thereby we can actually like do our transformation estimation. So here we're just printing that we're using RGBD Odometry. We're going to print the transformation, and then we're going to draw the registration results. So when we're going to draw the registration result, we're going to draw the source point cloud and the target point cloud, and then we also apply the transformation that we have estimated up here at the top. So the results here, if we have estimated the pose or the transformation good enough, these 2 point clouds here will actually like be aligned, because then we're just taking one point cloud, doing the transformation, and then it will be totally or like fully on top of the other point cloud, and they will be perfectly aligned if we have estimated the pose of the camera in the environment. So again, we're just going to do the same thing here at the bottom with the hybrid model. So we're just going to print out that we're using the hybrid model, we're printing the transformation, and then we're just drawing the results here again, where we just pass in the transformation down here at the bottom. I can see here that we're using the transformation for the color term. We need to go up and take a transformation for the hybrid term. So we're just going to copy paste that and paste it in here. And then when we run this block of code, we can now see the results that we got from the color approach for doing visual odometry that we got up at the top. So now we can see, if we look at the top here, we have now aligned the point clouds. We're now not like the blue wall here is not further back compared to the yellow wall. We can see that we're now aligned the 2 point clouds here. Because we've estimated transformation, we're just applying that transformation to our point cloud, and now we can see that we have actually like estimated a really good transformation between those 2 cameras. Again, we can just keep on doing the same approach here. I'm just going to show you here the transformation matrix here as well. So we have the rotation matrix here in the first like 3x3 in the transformation matrix, and then the last column here will be the translation between the 2 point clouds, or the 2 RGBD images that we got in from our camera. Again, the last approach here that we're going to take is the hybrid approach. It's just going to show the exact same thing. It's just 2 different kind of like methods. We can see here that we're perfectly aligned the wall, but we can still see here that the floor, the yellow floor here is a bit like a bit in front of the blue floor here. So again, this approach here didn't work as good with these RGBD images here, but again, you should just try out both methods, because some methods could be better for your approach. We can also see the wall here is a bit like further up here at the top compared to the blue wall. But if we just took the color approach here, we can see that the point clouds were actually like pretty good aligned. So we're actually like able to estimate the pose here of our camera by just using RGBD images. Again, you will just get your RGBD images from your camera, or you can use it for, like, you can implement it yourself with Open3D, do some conversions and so on. But again, if you just have a RealSense or like a PrimeSense camera, you can just get the output images from that camera, plug it into this Python script here, and then you can just do visual odometry directly with this Python script and your camera. So it's actually really easy to set up. Again, everything will be in my GitHub. You can just go in there, take the code, play around with it yourself if you have an RGBD camera, and then you can just use it for whatever application that you want to. So here we can see the transformation matrix. These are pretty similar. If you just go up here and look, like the translation is pretty similar, We can also see the rotation is also pretty similar. There is some differences here and there, because we can also see some differences in the 2 point clouds as well. But it's a really nice approach. It's really easy to set up. As we can see, we only need to call a couple of functions and a couple of methods here from Open3D. We just need the images, call a couple of functions, and then we actually have visual odometry. Again, I'm going to create another video where we're going to use more frames, so we can actually create a trajectory or a path from some different kind of consecutive frames. So instead of only taking 2 frames, we may be going to take a couple or an arbitrary number of frames. Then we're going to load that in, estimate the path and the trajectory of the robot where we have attached the camera on top of that. So thank you guys for watching this video here, and remember the subscribe button and bell notification under the video, and also like this video here if you like the content and you want more in the future. It just will help me and the YouTube channel out in a massive way. I'm currently doing this computer vision tutorial where we're talking about basic image operations, camera calibration, stereo vision, visual odometry, point clouds, how we can create our own point clouds, and so on. So if you're interested in that tutorial, I'll link to it up here, or else I'll just see you next video, guys. Bye for now.